Today we're going to talk a little bit about PCB specific IP. We got all of you guys want to give you some case histories. And then after that, we'll have done all the material that we need, just team-based learnings and presentations by you guys and partners. But before I start, I want to introduce you to a couple of people, one who you kind of know already. But I'm not sure that you guys are really aware of just how much effort goes into trying to make this course and build up all of the open source resources, the GPG, trying to develop apps that work, how to kind of connect with things. It's absolutely an incredible amount of work, far, far more than any other course I've ever taken. And the only reason that we're able to get to the point where we are is that there's been a big contribution from my whole group. And in particular, two people who are really important. One is Lindsay, who I think you have not met. Lindsay has just finished up her PhD, did her defense a little over a week ago, on looking at electromagnetics, okay, that EM word, in particular for steel case wells for problems that are associated with injecting material into the ground and trying to monitor them using EM. So it could be CO2 sequestration, it could be hydraulic fracking fluid, as people are going. All of these things, there's lots of really interesting problems. And Lindsay has finished up her thesis on that. But from the perspective of this class, her contribution has been really important. The read the docs, the GPG, Lindsay has spearheaded a lot of these things and kind of continues to organize the group. Savi, who has complemented her and has done a lot of the development of the apps, is been also just such an integral part of this whole thing. And in addition to that, we've got maybe 8 or 10 other people who've just been devoting time to trying to really make things work. So that, I don't know, I just want to take this opportunity to introduce you formally to Lindsay, Savi, who you already know, because these people have played such an incredible role in actually developing material in ways that hopefully you can engage in, so that you can see things, so that you can question, so that you can understand, and go out and use geophysics responsibly. So that was that. Now I have a couple of things. I want to kind of review certain things that we have been doing, and I'm pleased that there's at least a few people who have brought their signs up. So I'm going to ask questions. Michelle, what course is this? 50, good job. Liam, what physical property are we looking at?
For DCIP.
For DCIP, and in particular for this guy here, induced polarization. What's the physical property that we talk about?
Chargeability.
Good job. Okay, one more star. Now, for the more tough question, Arno, where are you? Okay, so I've got a fourth group. And I've got something called chargeability. And I'm going to put on an electric field, which I could get by doing the following experiment. If I have a battery, then I've got currents that goes like this. So I've got electric fields that are like this. So if I took this thing here, which is at a Porter scale, and kind of made it in here, then I've got this electric field. Okay, so now you want to sort of articulate what we kind of mean by chargeability and kind of what's happening.
So let's say if you have an electric field going that way, it's like if we had a positive charge on the left. And that means you have negative charges on the left.
Meaning like a big positive charge on this side here? Yeah. So I could make an electric field this way by having, a big positive, well, that's what I've got here, right? Big positive charge here. Yeah. So in here, I've got an electric field going back. Perfect.
At first, it's like in a neutral state, but as soon as you activate the field, you would get all the negative charges go on the left side, and all the positive charges on the right side.
Right, so the neutral state has to do, what are you thinking about with respect to that and what's in here?
Just sort them out.
Yeah, well, so in here there's a fluid, right? So there's fluid, positives and negatives, right? And neutral state means, it's electrically neutral, right? Okay, and now we put on the field, good. So let's suppose I do that, I just take that and I connect the battery, and so if I look at my current, my current is kind of going on like this, and what happens with the moment that I start to put this on? I put this field on?
Positive charges go on the right and the negative charges go on the left.
Yeah, so your positive charges here are going to go which way?
Right.
They're going to go this way, right? Because they're going to be repelled. And so you're going to try to put positive charges through there. And the thing about positive charge or any of these, they kind of can get blocked up by pores, right? So at the end, you might have a net accumulation of positive charges here and maybe negative charges here. And so the final state then is one in which effectively we've just got a big positive charge here and a negative charge here. And of course, that's like an electric dipole. So the moment that we have, like if we talked about a positive charge and a negative charge here, and if we're sitting out here, then there's an electric field that goes like this. So this positive and negative charge are going to give rise to electric fields, which we could then measure if we had, let's say, a voltmeter sitting on top, right? So if I was measuring the electric potential up here, I could do it. Now, how do we think about physically what's happening? If I didn't have any chargeability, then my voltage that I would get would go up to some value, have the same shape. If I turn the current off, it would drop initially down, and my voltage would look like this. So this would be my V of t for a non-chargeable system. However, if it's a chargeable system, so when there's no current, nothing happening. The moment that I turn the current on, there's going to be an increase in the voltage to bring back to this. But then these charges start to accumulate. So the moment the charges start to accumulate, my voltage is going to increase. And then, after a while, I kind of reach that sort of steady state. Can't put any more charges in. I can't continue to build these things up, right? Because if I imagine another positive charge trying to get away from this big guy up here, it gets confronted up here with a whole bunch of positive charges, it gets repelled this way. So eventually, there's going to be equilibrium. And so it's going to go up like this. And then the moment that I turn this off, turn this current off, I get a drop in potential, and then these charges simply decay away back to their baseline neutrality, and I'm back to something like that. The point is, when I go and I do the measurement, I see, first of all, this increase when I turn it on, but I also see like this decrease. The moment I turn that current off, voltage drops down, and then it decays away. So I know that all of these guys down, the effect, the measurement that I'm taking that is associated with that decay, those are all those charges. So they're somehow connected with this build-up of charge, and that's why they call this chargeability. So effectively, this is kind of acting like a capacitor. So the earth materials and capacitor. So anything that I measure that's connected with this is related somehow to chargeability. So I could measure a value at a particular time. I could measure an integral of things. I could do anything. It doesn't matter. It's all somehow, some way related to the fact that earth materials can charge us. So we showed last time talked about that, and then perhaps the thing that just is worthwhile repeating is that we collect the DC data and the IP data at the same time, right? It's the same history. I'm just measuring the voltages. So ordinarily for DC, I want this final voltage. For the IP, I want something that's connected with the decay. But it's still, it's still voltage measurements. And so I could plot them in exactly the same way as I do for a DC resistivity, and I get sort of an apparent, chargeability whose units are whatever the units of my data were. So remember I said you could take it in the frequency domain and you've got phase shift. So let's make this a little bit bigger. There we go. So we ended up here. So for each location of a current and potential measurement, I could just plot it at that intersection point. But now I'm actually plotting the chargeability data. But it's still going to be pseudo section. And then we just go along and we do exactly what we had done in DC resistivity, kind of a profiling and sounding method. So now I'm just computing all the IP data, and then I'm going to contour it up, and that's an apparent chargeability section. So you're going to hear two things: apparent resistivity, and also now apparent chargeability, all connected with the same experiment. So we saw examples of chargeable bodies with junk and get a pseudosection that looks really uninterpretable and is. So plotting of the data, you can't make a direct geologic interpretation. Here was that case where we had a couple of chargeable bodies looking like that. So we needed to further work with these data and invert them. So here was the ticket. We did this kind of right at the end of last day, and that is for doing the inversion of IP data. So you start off, first of all, thinking, okay, I'm in the DC mode, so I'm going to collect the DC resistivity data, and then I'm going to invert those for the conductivity model. Okay, so that's what we did in DC. I also said that this whole business of chargeability, so even though things can act as a capacitor, effectively what chargeability does is just sort of alter the effective conductivity. And hence, if we know what the conductivity is, we actually have a way of modeling and predicting the relationship between chargeability and the chargeability data. So we have to get the sensitivities, what's called sensitivities for this, and then that gives us the mapping that we need. And now we've got all the things that we need to go ahead and invert for chargeability. So what we've got here is actually effectively two physical properties. One is the electrical resistivity or conductivity, which tells us how easily a current can pass through something. And the other is chargeability, which tells us how easily it is for charges to accumulate inside that porous medium and effectively charge up. And then in the example, for instance, in this guy here, where the data themselves are completely uninterpretable, if we invert, we see the chargeable body that we're interested in. Again, it's not perfectly square. This happens all the time because we're looking for some smooth representation. And we also recover all these little geologic contaminants up here. Maybe they're graphites or clays or something like that are chargeable. And that is either useful or not, depending on your what you're interested in. So I want to now revisit a case history that we did a couple of months ago when we were doing DC resistivity. So I'm going to refresh your memories first on that. So this was a mineral deposit in Australia. So here's Australia, it's sort of way up here. It's called Mount Isa. And what we're going to do is to look at this now within the context of a DC resistivity and IP signature. So that background geology, just in simplistic form, it had some volcanics that were there. So these yellow guys here and the green guys are volcanics. There is a mineralized region in the purple here that we're interested in. It's a mountain over the horizon. There's sort of mineralizations possible within the context of that. And really the end result, or the end question, is that can a conductive and chargeable unit that would be potentially mineralized, can they be identified if they're sitting in a whole bunch of siltstones? So you've got siltstones in the background with these blues in here. And the question is, can we actually see some mineralization? So we look at the physical property table. We have all of these different rock units, and there's both conductivity and chargeability. We did the conductivity, and the volcanics are really low. They're really low conductivity. They're very resistant. The siltstones, which house the mineralization, have just got moderate conductivity. The thing that we're looking for, the Mount Nova horizon, has actually got a high conductivity. So that's good. It distinguishes it from its background host, the siltstones and the volcanics. The fly in the ointment here was that there was also another unit. It was called a breakaway shale or black shale, and that has a very high conductivity. So that's kind of what we were up against with the DC resistivity. If we look at chargeability, we're actually in a better location here, because all of the units have really low chargeability except for this Mount Nova horizon. So the good news is that the thing I'm looking for has got a high chargeability, which distinguishes it from everything else. And it's got a relatively high conductivity, which distinguishes it from a lot of others. So what did we have? Remember we had like 10 lines of data. So the data were acquired in sort of pole-dipole fashions along these lines. The geology is kind of north-south, so being perpendicular is good. And then the apparent resistivity pseudosections are given like this. So this was all with a pole. So remember how I got a pole? We always have 4 electrodes, but if I take this electrode and I put it way in hecagon over here, then effectively I've got a pole dipole. So there's 10 different pseudosections. The red indicates that there's something that is highly conductive. So you see there's something in there. Always you get more information by changing how you're sort of lighting up or how you're exciting the Earth. So in this case, instead of the current electrode being here, let's plunk it over there. If we do that, we get very different pictures. They look something like this. So now we've got a lot of real red. But at the end of the day, I've got 20 images here, and really there's only one geology, and that's what I'd like to get. So Now we take these data, we put it into the inversion. So the inversion is such that I just take this big mathematical cube. It's got, I don't know, in this case, maybe 600,000 or 700,000 cells. And then I'm adjusting the values, conductivity in each, so that I fit those data and get something that's as minimum structured as possible. So just to remind you, so this is that conductivity cube. The red is high conductivity, blue is low. So you can see there's definite regions of high conductivity. Slice from top to bottom. We've got some big thing coming in here, maybe a little guy coming in there. Rotate it around, progressively increase the value of the isosurface such that everything that has got a value less than that is invisible. So we're left with the regions of highest conductivity, which is this great big linear feature that looks like that. And then there's a couple of little guys over here. So the big takeaway thing here geologically is this large conducting unit up here. But unfortunately, that was not really of interest from the mineralization. So it was very interesting to the geologists because they want to know where this guy is. But from the mining perspective, it wasn't. So it's kind of like one of those good news, bad news things. But also, we're not finished with this case history, right? Because remember, the other physical property that was germane was the chargeability. So now let's go to look at the chargeability data. And this is what we see. So now we've got the pseudosections, there's a dipole pole, and here's the pseudosections. They don't go all the way down because the signal that we're looking at here is already really small. And so you simply can't take extraordinary long offsets and get a good signal. At some point, they just get cut off. So that's why these guys are truncated a little bit. But anyway, that's data. And we had 20 of these, and now we do exactly the same thing. Except what we first do is we take this conductivity structure, and now we compute the sensitivities for that. And now we're going to take that and invert for chargeability. So remember that two-step process. So now what you're going to look at is the same kind of thing. It's a cube prism with, again, same number, 600,000 cells or whatever, but now of chargeability. So we're going to step through and look at that particular. So the red is indicating stuff that's chargeable. So this is what you now end up with. It's very different than the previous example that I showed with conductivity. But we have, importantly, this very large region up here, which is chargeable. And in fact, if we kind of do the comparison of these guys, we've got a horizon here, and this is the Mount Noblet horizon, comes through, snakes through like this, and this is the guy that's chargeable. Remember, he was also supposed to be conductive but not superconductive, and if we look over here on E, you see that, yeah, there is some manifestations of conductivity. This large conductor that we had through here, that black shale unit, if you plot that on this line, kind of comes over like here. So by and large, there's no chargeability associated with this black shale unit. So this is, I think, a tremendous success story. I mean, they drilled this and they got mineralization. Interestingly enough, when Lindsay, in this case, and I were in Australia, we were giving this discourse on electromagnetics. We were in Adelaide, and we showed this case history, and we said, you know, is anybody here kind of familiar with what this area was? And interesting enough, there was a guy there from who previously been with Mount Isa. He's still working at that mine. He's the chief geologist there, and he said, "Yeah, you know, we're actually still working on this." And then I asked him. I said, "Well, what about this guy in here? Because it's chargeable. You know, is there anything, you know, potentially of interest here?" And he said, "Well, it's funny you should ask, because that's one of the things that had caught their eye, and they actually are going to go back and drill that." So I think the usefulness of geophysics and kind of that ability to get like three-dimensional images of the subsurface that might help you understand what's going on. Anyway, so that was kind of it. I have two more things I want to do. Any questions while I change gears here? Okay, so this is a story that I think you might find very interesting. There was a student by the name of Kevin Fan. He did his bachelor's degree in geophysics. He finished up in spring of 2018, so not very long ago. He was just really interested in geophysics, and he wanted to kind of do something that was really useful, that made an impact. And the thing for him was that, excuse me, can I ask you to put that away, please? Just pay attention or whatever. What made things kind of interesting for him was the potential for doing something that was kind of humanitarian. And the thing that caught his mind was the potential to go to Myanmar, for people who know where that is, and actually work on water projects that are there. So here's Myanmar. The state of Mon is where he was in. And the thing that is important there and was kind of in the purview of GeoSci, the Canadian Union of Students Overseas, which is a humanitarian group from Canada, was the opportunity to go there, collect data, interact with local people there, and see if it could make a difference. So this was his mission. And here's the map for where it was. So he's going to actually be in this particular province here. And this is the reason that he became very kind of excited about this. So in Myanmar, they've got about 2 months of the year where their wells just dry up. And that means that, you know, people have to go and you know, collect water. Usually it's the women, okay? It's the women who do all that hard labor. So not only is that a lot of hard labor for them, it takes them away from the opportunity to be educated and to, you know, properly raise children, and that has all sorts of negative downstream effects. So there's sort of an estimated, you know, 25,000 villagers here that each year are disadvantaged because of lack of water. And when they don't have water, then they have to rely on donations of water. And currently, on average, the amount of donations that they get either through government or international agencies is about 4 gallons per person per day. So you might think about how many gallons of water you use per day, you know, from showers to flushing toilets to dishwashing machines. So they get 4 gallons per day, and often they have to walk a long ways for that, carrying that on their head. The minimum in UN standards is even 5 gallons per day. So they're not even making the bare minimum. So that motivates the somehow trying to do something with it. There were kind of the story so far. Japanese agencies had gone there. They were using DC resistivity in a Schlumberger mode, which I know all about, and their goal was to try to find the depth of the water table and to see where they could find water. Now, the Japanese went in, they collected some data, and it looked like DC resistivity was going to be useful, but that was the end of it. They didn't train anybody, they didn't leave instruments there. There was no cascading benefit effect later on. The kind of data that they got, and I'll show you this. So this is a sounding curve. So you're now all familiar with that. So this is the length scale here, like AB upon 2. Here's your apparent resistivity. So these numbers here will show you, might resonate with you. And the fact that it's going down means that there's something that has a lower resistivity here. And if you looked at the kind of the geologic log, there's potentially 2 aquifers, but there's an upper aquifer and maybe a lower aquifer. All of these are in the top 150 feet, something like that. And so you want to try to see if you can potentially find them. So what was their goal? Given this kid, I mean, the only real kind of practical geophysics course he'd had was 350. Came into my office, he said, look, okay, I think maybe we could make some equipment, take it there, train people, and show how to use geophysics. And he says, do you think I can do that? And it's just like, I'm like, well, maybe, I don't know. It's bad enough doing that if you've got support, and kind of if you're just parachuting into Miramar, you don't know the language, you don't know the customs, you don't know anything, how anything works. It's kind of amazing. But what he wanted to do was to build instruments and to train people and show them how it would work and actually make a difference. So you need to connect up with the groundwater hydrologist to try to find out something about what is needed for hydrogeologic interpretations. And as I said, there's both a shallow aquifer and a deep aquifer that they felt had kind of gone north-south along that state. Target of interest, 2 things. Very simple. What's the depth of the water table? And what's the depth of the bedrock? Okay, so that's 2 very explicit things. And notice, I had pointed out, but Kevin is doing everything in a 7-step process. The very first part, that was all set up. And now, okay, we've got the setup, we've got the problem. What's the physical property? Well, it's electrical resistivity, and those are going to be our goals. What does he really want to do, and what's the rationale? Needs to have cheap equipment. So if you go to a company right now and try to get an off-the-shelf DC resistivity IP system, you're going to be looking at maybe $25,000 or maybe even more, right? So that's simply way, way too much money to think about having multiple systems that you could leave there. So he wanted to develop an inexpensive system. And there's a guy by the name of James Clark who has been doing a lot of humanitarian work in Africa. He's got 7 or 8 different kind of groups of people in various countries in Africa working out. And he designed and built an inexpensive DC resistivity system. It's about 50 times cheaper than a commercial device. And that's kind of what you need. So if you're going to look at design considerations, you need to have something that's like 50 times cheaper. It needs to be simple. It needs to be really robust, right? Because it's going to be dropped and mishandled and all things. And it needs to be light, compact, because you're going to be carried. So you can't have massive batteries. So that's what you need to do, and this guy was able to kind of put something together for under $1,000. So what Kevin did, like, okay, he gets the circuit diagram for this thing. I mean, he's got no electronic background. He's like, okay, got a circuit diagram. Finds another guy in physics, and they start to try to put this thing together. So we got a car battery, we got an inverter, we got some switches, and you're going to hook all things up like that. So this is now what it's starting to look like. What you've got here, these are spools of wire. Okay, here's an inverter over here. We've got some voltmeters and current meters over here, and some clamps. And here's your stake. So these are lag screws. So they're 24 centimeters long. So that's going to be your electrodes. As you go in, you're going to have two of them, two currents, two potentials. And then here's this measuring box, and I think this says a lot. Blood, sweat, tears, and solder. Kind of putting it together. And then here's his switch box that goes to the inverters. At the end of the day, you just put it in a little suitcase type container. You got your tape measures here. Here's your wires. Here's your equipment. Strap it all to your back. Off you go. Got an inverter from Kenya, and went out. And it worked. It collected data, right? So here's Kevin's data on the left. So this is apparent resistivity. So this is a winner array. And we're looking at the A spacing here. So that's 1. So 1 meter, that means that, your system's like this, right? And by the time you get out to here, you've got, 300 meters between your outermost electrodes. So if you look at this, it's the apparent resistivity, that's 1,000, that's 100. That goes up like this. Now if you look at what the Japanese got, same kind of thing. So it kind of goes up. So here's 1,000, here's 100, so it's going up, and it's down, and then it's up. So the numbers are actually pretty comparable. So he's able to, okay, I went to the same location, put up my instrument, measured my voltages, converted them to apparent resistivities, I get out the same numbers as this professional organization. So it's like, okay, good job, Kevin. So then you got to train people, you get locals, they're enthusiastic. Here's your equipment. And then here's his electrode geometry. So it's basically, you'd recognize this. That's a winner, right? And then you go out, collect some data. Every time you put a measurement in, you measure the voltage, you measure the current. That's enough information to give you the apparent resistivities. And now you've got different apparent resistivity, 42, 36, 19, 14. So now you want to take those and invert them. The inversions I've showed you are, have been through kind of one methodology, but you can also just do like trial and error types of things, sort of what I call Monte Carlo inversions. And that's what's done here. You specify the number of layers, and then you've got this sampling algorithm that just changes layer thicknesses and resistivities, and it can generate zillions of these things, and then you find out which ones that acceptably fit the data, and here's a result and fit. So the blue is the predicted from this, and the red are your measurements. So you've actually done a pretty good job. And then you look to see what the results were. We talked a lot about non-uniqueness, right? So you can get all kinds of trade-offs between layer thicknesses and resistivities. But at the end of the day, with all of that Monte Carlo sampling, you got a layer 1 that is confined. It's got resistivities between maybe 600 and 1200 or 800 or something like that. and then it's got a particular thickness to it, same with layer 2, layer 3, layer 4. But you can see that you've got sort of resistive, conductive, resistive, and those then can get translated into likely geologic scenarios of layer 1 being weathered gneiss, layer 2 might be like sandstone, option 1, option 2 or 3 have slightly different geologies, but the idea is to take these and interpret them to be something that is relevant to the geology. And then of course you can always sample after that and see how well. So that's basically what was done here, is looking at some of those different models and seeing what the data would be like, just to try to kind of nail down uncertainties. So here's his synthesis, right? So we've gone through all of the 7 aspects. Okay, we did the setup. Okay, what's the problem? All the information, and you saw like most of the slides were actually involved in that, trying to figure out, okay, where are we in all that? And then we've got what's the physical property? Okay, conductivity or resistivity. What's the survey? Well, in this case, you choose DC resistivity, but you could have done a frequency or time domain EM. That would have been a possibility. Equipment's more complicated, it's more expensive, but it might actually be really fruitful. So you could kind of think, okay, I'm going to hold that in the back of my mind, but I'm going to go out and do DC resistivity. Okay. Then you go out and you collect data. Well, actually, there was an instrumentation part in there, right? What's my survey? You know what the survey is, but shoot, I got to build the equipment. So that's a hard one. But he did. And then go out, collect the data, Wenner array, different spacings. Processing, I'm just going to do forward modeling and inversion. Interpretation, it's got a variety of geologic, a variety of models with different geologies that are attached to them, and that's his end result. And the last is the synthesis. So it's worthwhile just reading a couple of things that he's got. So first of all, he recognized this is an ongoing project, not enough data that has been collected. And here is actually where Soggy and Lindsay kind of return into the scene, because what we're trying to do is to get a grant from Geoscientists Without Borders. I'm not sure whether you know about that, but there is Doctors Without Borders. Well, there's also Geoscientists Without Borders, and they give out grants. We are applying for one. We should actually hear moderately soon as to our success, but that would provide enough money to build equipment. Kevin wants to go back out there. He wants to train. He wants to train people on how to use the equipment. He also wants to train people within their government organizations on how to think about this, how to use it. So you can imagine from Cuso, that was actually part of his mandate. Build equipment, go out, take data, train people on how to acquire data, train people on how to use data, and train people on the sustainability to keep this whole thing going. An undergraduate, not bad. So we're trying to get this grant to actually go about and do this, and part of the main contributions here is actually with Soggy and Lindsay, and actually Kevin is going to come back in February. He's going to work with us at the Geophysical Inversion Facility and develop open sources so that there is training material and there is interpretation material that can be used not only in Miramar but elsewhere too. So this is ongoing. Okay, he does have another field campaign coming up to do probably 20 or more sites, and really then try to get locals to come in and just see if you can get somebody to do some drilling someplace. So this is a bit risky, right? You're going up, you're collecting data, you got interpretation, and now you're trying to convince somebody to come and drill to test your hypothesis. So you kind of want to be right. Anyway, let's see how that goes. And then he wants to upgrade the equipment because his current design couldn't quite get down far enough. Remember, in order to see down 30 meters, you need to have electrodes that are at least 90 meters apart, maybe a little bit more. And that means you need to have more current, and you're limited to the size of batteries that you can use, And so he's back in the planning stage, trying to extend it so he could have 600 meters of wire and get higher precision multimeter. So, and this slide I was actually quite appreciative. So this is actually Kevin writing. He says, "Thanks 350 crew for your interest in my project." So that's Saki, Lindsay. Yep, my interest in environmental geophysics got started in 350. And he's speaking now to you. He says, "You're fortunate to get exposed to so many cool applications of geophysics. Feel free to get in touch if you have any questions about this project, Myanmar or international volunteering." So there's your challenge. Okay, any questions about that? Yeah.
How long, like Mike said, how long was he there? How long was the whole project?
Well, he was there for close to 8 months. In fact, he's probably still there for another week, collecting a little bit and doing it entirely on his own nickel. I mean, there's just nobody paying him to do that. I mean, he is just incredibly motivated. And then he's coming back, and he'll be here for a couple months, and then he's going to join us at the Geophysical Conversion Facility, spend 6 or 8 months here. At that time, we hope that we'll get this grant from Geoscientists Without Borders, and then be able to take it one step farther. So that's the plan. We'll see. Yes. There is one thing. I'm not going to start it right now. I'm going to slip it in someplace, and that is the use of IP for waste dumps. You'll see a bit of that in the team-based learning, but I've got a few extra slides that 5 minutes just kind of show you how IP is, I think, perhaps especially tuned to try to find the old waste dumps that are around. So I think coming up next, we've got a TBL on Wednesday. Yeah, so TBL Wednesday is for the DCIP. And then on Friday, this is, what was on Friday?
App contest.
Yeah, by Friday, you need to hand in your individual apps, and then we'll have a TBL where people can kind of work together. So the idea here is everybody hands in something, okay? And then as a group, you get a chance to take a look and see, okay, which problem, which app is, going to make a stellar presentation, and then those will then begin on the Monday. Yeah?
For the submission, do we hand in a physical copy, or is there an electronic submission?
It'd be electronic. I guess we need to hand out some more explicit details about how exactly you do it. But basically, you put it onto PowerPoint slides or Google Slides or something. So we don't want big, long treatises. If there is a document, a paper, for instance, a case history that you're extracting information from, we'd really like to have that attached just so that we have additional context. But the idea here is just trying to identify a problem that you have or that's of interest to you, and a particular geophysical survey, and then see, okay, if there's a specific question, do we have an app that can help answer that? Or if not, here's what you should have. It would be really nice to have an app that did this.
Yeah, so please, 7 steps, can you comment?
Oh, yeah, so everything put in a 7-step procedure, right, for your hand. Thanks. Okay, good. Thanks, guys.